The next two sessions, which I think is kind of the highest demand right now, is how do we build our robot past flex, for example. And Steve and I already talked. I think you should start in the building the flex robot, seeing its limitations, how can you improve and make it better. But a lot of teachers ask the question of, well, how do you do that? I don't know how to make it any better. And I see these drivetrains where the robots are driving left and right or strafing. You were talking about Omni wheels earlier. What does that work? How do those come together? So one thing I didn't mention, that Steve is actually, is it called Master Builder? Super user. The Lego. I didn't want to. I can't believe I brought up that word around here. But if you've been to Worlds, they've got all of those really neat kind of Rube Goldberg contraptions and kind of the latest and greatest of the VEX IQ stuff. So that's kind of Steve's world. But then Paul and his son Dane, right? What grade are you going to be in? 8th grade. They're going to be helping out with the kind of go over things and strategies they use for building the robot, and then we'll go right into programming. And like I said, when we go into programming, we'll talk really about starting at the basics of downloading the software to using the software to program your robot. So I'm going to hand it over to Steve, Paul, and Dane. Let them go. Did you need me to show you anything of this or PowerPoint? PowerPoint it is. All right. Off we go.
So, a couple things we want to sort of look at. Some of the different, different bases. As I said earlier, we have a couple hours to show you stuff that you're going to spend the entire season teaching the kids. So we're going to try to cram a little stuff out in here. This is one of the more common types of drives, the tank drive. I had a friend from Australia say, we don't call it a tank drive, we call it wheelchair drive. Okay. Where you've got a wheel on each side, or a motor on each side, driving at least one wheel on each side. The basic robot, the Flex, is geared so it's driving both wheels on either side. As you see, the problem with that is that you can't move sideways. And George was showing a little bit earlier how sometimes when they turn, they'll chatter a little bit because of the way the wheels are actually forced to slide sideways. There's a couple good things and a couple bad things about that, which actually I think I'll talk about here. Yes. A couple things you may want to do with that. With the standard robots, they're fairly narrow footprint. The width, not very wide, not very long. They can't really make it much longer than this just because of the parts that they have available in the Super Kit. The width, again, it's hard when you're constrained by that. One thing that you have to consider, or you need to tell the teams to consider, is how easy the robot is to drive. That's something that's going to be very important as they, with the 4th, 5th, 6th graders, is actually being able to drive the robot. Something that I can tell you, Dane here is going to make a robot that's pretty fast. It's also going to be very hard to control. And what you see when you go to your tournaments, you'll see, oh, they've got all Omni wheels on it, and it can drive sideways, and it can do all sorts of stuff. Those robots are actually pretty hard to control, especially, again, with the younger kids. And so it's not always the best bet to put as many Omni wheels on this as you can. You know, as George said, if you put Omni wheels on the front, it will turn faster. Do we want it to turn faster? That's a question that we need to ask, because now when I try to line up these hubs, the robot's turning very fast, so it's going to spin around, and I've totally missed my target. And so, you know, then I turn back the other way, the robot turns nice and fast, and I've missed again where I'm trying to go to. And you see, if you have the rubber wheels on there, it'll turn slower, but that may be what we need for the drivers we have available. We want it to turn slow enough that he can get it lined up just right. That's something that the kids need to think about, and you want to kind of help them understand it's not always best to have a robot with 4 Omni wheels on it. because it may not go exactly where you want it to. Again, with the Omni wheels in your programming, if you want to program the robot to drive straight forward, and it's got Omni wheels, oh, let me back up a second. Omni wheels. If you haven't seen them, this has Omni wheels. The thing about this is these wheels will slide sideways. This whole robot just has 4 wheels on it. It can actually slide sideways on the field. So if it's right here, it can slide sideways. There's actually no motor or anything that's causing it to do that. That makes it so that if I'm trying to drive around one of these pillars, it'll just sort of scoot out of the way and not get stuck on the pillar, which is great in that it's more flexible in what it can do, the way it can drive around. But again, if I just want to go in a straight line, it can be more difficult to drive straight because the robot's going to tend to slide sideways a little bit. With one rubber wheel, with a rubber wheel and an Omni wheel, again, the robot's going to be a little more loose in how it turns, less inclined to drive straight. If you have 4 rubber wheels, the robot wants to drive straight forward. You have to sort of force it to do the turning. Slows the robot down a little bit when it's turning, but it drives in a straight line, which is great if you're trying to program the robot to drive straight across the field. If I wanted to get from this end down to that end with my program, where I just tell it drive straight forward, if I have a bunch of Omni wheels on there, it may not do that. It may tend to go off the side a little bit, or if I just have 2 rubber and 2 Omni wheels, it's able to turn very easily, maybe more easily than I want. This is the kind of thing that you really have to consider, the kids have to consider, you know, who's going to drive the robot? Can they drive it? And what you can see is if they're driving the robot and it seems to overshoot a lot when they're turning, the robot's turning too fast. How can we slow it down? So there's a few things we can do to slow the robot down, or speed it up if we want to. One of the things, when the robot turns, basically it's got a center of rotation right in the middle. So the whole robot's turning around that center point. If I move the wheels out farther, if I make the whole robot wider, these wheels have to drive a larger diameter. So it's going to turn a little bit slower. It's going to drive forward and backwards at exactly the same speed. But to turn, because the wheels are farther, they're doing a larger circle, they have to cover more distance, it's going to turn a little bit slower. Something to consider. If you want to slow the robot down on the turns, you can make it wider. That'll also make it more stable. So it's going to be less inclined to fall over sideways because it's got a wider footprint. So if you do have a really tall robot, if you make it wider, it's going to be a little bit more stable, side to side. Same thing happens front to back. These robots, they're designed, the standard flex stretch robot, designed with this little thing sticking out the back. What that does is it keeps it from falling backwards. Not actually there to do anything fancy aside from when you take off forward, that piece hits the ground and the robot doesn't fall over backwards. This one also has these things sticking out the front to keep it from falling forward. Again, not necessarily to help it move, but to help it keep from falling over. If you can make the robot longer, then it's going to be more stable front to back, the same way it is side to side. Making it longer, one of the easiest ways to do that, this by default has 3 gears on the side, the 2 drive gears and the one in the middle. If you put 2 more gears on there in the middle, so you have 5 across. Relatively simple change to this, but it's going to be longer. It's going to make it more stable front to back. Now what that also does is make it so that these wheels, when it's turning sideways, they have to scrub sideways even more. This, if you make this wide enough, then when it turns, these 2 wheels on the side are actually mostly going straight, forward and backward when they turn. There's not a lot of sliding. But if I make it so there's 1 wheel here and 1 wheel here, then when it turns, this front wheel has to do a lot of sliding. Okay? So that's a little bit in how the wheelbase can affect its moving. making it wider. This is the kind of thing that we can experiment with. You know, is there a way to make this robot wider? And does that make it turn better? Does it make it easier to drive? You can try changing out, put on the Omni wheels. Is it easier to drive with Omni wheels? Or does it make it really hard to drive now? Because it's moving all over the place. A lot of the 8th graders really like the robot that moves really fast, turns really fast, and they're able to control it. Some of our 4th and 5th graders, not so much. One of the problems that comes up is, well, we have one guy on the team that can drive it. Well, that's great, but we also need 2 drivers. And so can that second guy drive it just as well? We'll talk about that a little bit more with our team building. But that's one of the things you have to think about, not just what that one kid can do, but what the team can do. So we can look at different wheels. We have the length. We have the rubber wheels versus the Omni wheels. And how that, can we see how that controls how that can affect the turning of it? Any questions about that? No? Awesome. Does anybody understand anything I just said? So along those lines, these sample robots that they have, again limited on the parts that they can use, you'll see these wheels are kind of wobbly. That means the whole robot, when it drives across the field, not going to be extremely consistent when it drives from here to there. Because, you know, maybe when you set it down, the wheel was off a little bit, or you just did a turn, and that affects the way it drives under driver control. It affects it a lot more under programming, where these wheels are too wobbly to be consistent, so you're not going to get consistent runs in programming. So what you can think about is with the axles, the drive axles, a lot of times you want 2 points where the axles connected. If you look on this, there's sort of just 1 or 2 beams really close together that the axle's going through, which is what gives the axle a lot of play. If you look at this awesome robot, it has 1 beam on either side of the wheel that's actually holding the axle. So that makes it so that those two points are pretty far apart, about as far as they can be. They're on either side of the wheel. Sometimes you'll end up with the standard clawbot. They're both on the same side of the wheel, but they're not right next to each other. There's about 1 inch between them. The more you do that, the more stable it is. See, this wheel doesn't really wobble very much at all. The axle's pretty solid where it is. That's a good tip for building a sturdy robot with a sturdy frame. If you can get those 2 connection points farther apart, it'll make it more repeatable in your driving and your programming.
Will this help or not?
Yeah.
I'll throw it up.
Will that help?
You
You
can
can
play.
show it on the screen, yeah.
Oh, you want to see stuff? Awesome.
See if it looks nice.
That is our
That's
pen.
very helpful, thank you, that pen is great.
Yeah.
I don't know if you'll be able to get it under there, or you can rotate it.
Yeah. There you go.
Can you see that? Wait a minute. He'll fix it, it's fine. Hold on, let's come back to this one. As I said with this one, you can see here we've got 2 beams that are right next to each other. That the axle goes to the drive gear. Right next to each other, not much support. That's what allows them to wobble more than what we want. And over here we have the 2 beams on either side of the wheel. One inside, one outside the wheel. That, well, there's not much wobbling it can do. That helps to make the whole thing more stable. This one of the things I like about this, which I can't show in this because it's too small, this has a square that goes all the way around the robot, which makes it so that it's got a pretty sturdy frame. Set the back. which has got supports across here that make it sturdy to hold the side pieces in place.
What design name is that?
This is designed by, this, I think he started with the stretch
It was the flex spot,
flex spot.
right? And then it's just evolved to improve.
So we saw earlier, we didn't actually see the flex spot, but this has the hook on it that doesn't really do anything. Doesn't have an extra motor or anything on it, able to pick up the hubs. And we just modified it so it could reach higher and had omni wheels, right?
Yeah, that's all that was done. So the vertical mast,
Taller with a longer arm so it can reach the bonus hubs.
and then the wider and longer wheel base.
Yeah.
And omni wheels. So the omni wheels are important. Well, you'll find even more important of that flexing of the axle. When the axle flexes and the wheel twists like this, the rubber wheel, it still pretty much maintains contact with the ground. It doesn't clunk a lot. But the omni wheel, because it has those every other rollers, it goes clunk, 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 and it really becomes a bad rolling situation if the axle is not horizontal and supported on either end.
If this is driving on either the outside or the inside, it's just gonna hit these wheels, it won't hit the other set of wheels, which will give it a lot of vibration as it's moving.
And really, I mean, with that other design, if you look at it, if you took this beam off, this axle and this wheel is being cantilevered outside of the frame, and that's where it starts to bow and flex. And when you look in the back of it, sometimes you see the wheels are actually bowed out. On this frame, sorry, I can get back. That was actually a great. On this one, I mean, if you look, this is really just a simple exterior frame going around the outside perimeter of the existing cantilevered robot. I know that they have a chain drive on here. It's not something that you have to do. You can still keep those gears that you have on there on that 1-to-1 gear ratio. But they're just creating a frame on the outside so that this axle is not hanging and reduces as much flex as possible. And that's going to come on, as Steve was saying, huge when you do autonomous mode to go straight, and your robots tend to want to drift left or right. If you can keep those axles and reduce as many variables as possible, that's going to really try to make things go true straight left and right.
A couple other things to show you real quick. Here's another chassis design. This essentially has the four wheels, has the two drive wheels like we saw. Figure out how to get it right.
Switch it towards the, yeah, there.
Okay. So this is a lot like the Clawbot base, where it's just a rectangle. It's got two beams on the side. Must be a fingerprint on here. Two beams on the side that hold the gears. Again, like I said, it's got 5 gears to make the base a little bit longer. It's got 2 rubber drive wheels and an extra omni wheel, which are all powered, which gives it the length to make it stable. And it's got a lot of width to it to keep it, again, stable so it can turn well. This set of omni wheel, or the rubber wheels keep it so that it's fairly easy to drive. So it's not going to turn too fast. We could put omni wheels on the back, make it so it'll turn probably quicker, maybe quicker than what we want to be able to line up with whatever goals we're trying to hit.
Actually, that's a good example of where the contact points between the axles are here and here. They're still on the same side, but they're gapped by enough to where this can't do a lot of wobbling. Whereas we saw in the flex spot over there, they were right next to each other. So you imagine the shaft fits kind of loosely through that hole. If the hole was small, the shaft could wobble a bunch in the hole. If you spread the hole out wider, you can much more support for the shaft and more wobbles.
Go back to the presentation this last.
Yeah.
I don't know which button it is. So that's one of the standard robot designs. Oh, good. So,
Can we go back?
yeah,
Really easy.
we'll go back one more.
I like doing stuff, so I'll
Awesome.
hang out here.
About time we got you doing something.
Thank you.
So this has a similar design with the wheels. One of the things about this one is slightly different is the gearing in here. This orange gear is actually a bigger gear than what we saw just a minute ago. Because this is offset in just a way, and it's kind of hard to see from this angle, but I'll show you something else in just a minute. See how the orange gear makes it a little bit longer?
Yeah, you can see.
Can we see that?
All of these are the exact same size. All of these are the exact same size, but that orange one is the, at least 40, and this is a larger gear.
36 and a 48 tooth gear.
Yeah, there we go.
Just a little bit larger.
And that's the out, so this would be your drive gear. This is the output axles going to that orange one right there. And I'll let you.
So the thing about this, it's a kind of a simple change, you know, not a huge difference from that robot, but this one's actually going to go a lot faster. Reason being the 48 tooth gear, go ahead. The 48 tooth gear, the top picture here shows the gearing on the standard base. And if you move them apart just a tiny bit, which you can see where the axles are in the bottom picture, I think you can see it, where the red axles go through. Move it apart just a little bit, you can fit the bigger gear in between. And it makes it go
What's
about
that, Dane? Do that.
It's 4 to 3, is it 3 to 4?
48. So
48,
36.
36.
48, they're about 4 to 3.
We don't use those in that big numbers, we use 1, 2, 3, 4, 5. Or they divide by 12. So 48 is at 4, and 36 is at 3. So that's a 4 to 3.
4 to 3.
So how faster? Who's faster?
About maybe 33% faster.
That's it. There. So because you're driving, the drive motor is on a 4, and it drives to a 3, 4 over 3 versus 3 over 3.
Steve, just real quick. There are videos, you know where they're at? There's videos that you can show the kids that we use in our camp on, is it on VEX IQ site? But that will go step by step talking to the kids about the gear ratios and how to.
Robot Events has links to, you can also get them on YouTube.
Is this what you're talking about?
Yeah, somewhere in there are little videos,
So,
maybe off to the side.
I mean, the analogy I say is think about a bicycle that has multiple gears. When you're in first gear and you've got this little tiny gear, you can pedal really, really fast. You're not going to go fast, but you can go up hills easier, meaning you have higher torque. But when you put that in the 10th gear, it's really hard to pedal, but you can go a lot faster. The difference between these robots is, at least it hasn't been invented yet, but we have a single speed transmission, meaning we are not switching from low to high gear in these yet. Why haven't you guys figured that out yet?
It has been done.
You
have a two-speed transmission? I just haven't seen it yet.
Well,
So,
question Lori.
We were thinking about it.
what I'm getting at is you need to figure out the current setup you have is called a 1-to-1 ratio. The output gear is the same, the drive gear is the same as your output gears on your motors, or on your wheels. This is going to give you, you're going to lose power, but you don't need to really push much on here. You're not pushing on the robots, but you can increase speed. And as Kathy was saying, there is I'm just under VEX IQ's website, and I think it's under Educators Curriculum.
Somewhere in there, there's little videos.
Yeah,
You have to click around.
they kind of show you just the difference between low gear, high gear. Sorry. There we go.
So the whole understanding of gear ratios is a really good thing to help the kids understand how that can make it go faster. And what I want to point out, this is a good, simple gear ratio that they can put in. They'll make the robot go a third faster. Then we back up and decide if they want it to go that fast in a straight line, or if they want to keep it at the speed that it was. That comes down to.
So let's extrapolate this. If you can go a third faster, you can go twice as fast, or 6 times as fast, or 100 times as fast, right? Right?
Yeah.
Can you?
Well, actually, when you get to, we actually figured out this when we were messing around with the VEX little propeller stuff. They added these little propellers, so we just wanted to figure out how fast we could spin it up. So we had a thing go 1 to 50 or 70, like 75, and it got to the point where it couldn't even spin up this little 1 ounce weight. Just the torque was, there's so little torque that it couldn't even spin itself up.
Right, so you are limited by the amount of, the correct terminology is power. The battery and the motor can deliver so much power. And power goes into either speed or strength, but not both.
Yeah.
So it's a balancing act, right? You can go fast and,
Weak.
or slow and,
Strong.
you can't go fast and strong. Yeah, you can go slow and weak.
So the best you can get that is 1-1. The best you can get that is 1-1.
So always, in all implementations of motors to do a job, be it a robot or railroad applications, is that you've got a limited amount of power to spin, and you can even use that power to go very fast but weakly. Sometimes you do that with like shooters. You'll spin a set of wheels up and throw a ball through it, pitching machine kind of things, right? It's weak, so it takes a while for them to spin up the wheels, which don't even weigh that much. And then, or you can go slow and strong, like a crane, where you got a motor that's working and it's down geared a whole bunch, and they can pick something up very heavy, but it can't do it very quickly. So slow and strong versus fast weight. That's a great teaching lesson for all the kids in all robotics. How well can you take your limited amount of power and apply it either fast and weak or slow and strong? And the most efficient balancing of that will get you the best performing robot.
And all of you guys actually used that last year with StretchBot because your lifting mechanism, if you remember, was a really, really tiny gear going to a gigantic gear. And all that was doing is it was allowing you to pick up that really big, I mean, this is a pretty big, heavy, you had a motor on here, you had this entire lifting and the 4-bar lift on here. I mean, there's a lot of parts on here, and that's why you had 2 small drive gears going to these big gears. You can lift a lot with this, but it's not going to go up. Yeah, you're not going to be going up and down really quickly, which is not necessary. I also just disengaged the axle. But
You broke it and
yeah.
Awesome. So point is, this is a simple option for gearing. There's a lot more they can do. They can make you go a lot faster. It will start to lose power and it won't respond very well to what they're doing. At this speed, the motors have enough power to drive the robots that they're going to be making. Any questions about that? No, I'm explaining stuff really well. Or they're just not paying attention. There's a couple different types of drives. What we've been looking at is a tank drive and wheelchair drive. This resource, this link has a really good description of some different drive systems, which we'll go through real quick. But this link is available in the presentation. One of the more common ones that we'll see in a lot of events is the H drive, the 5-wheel, where it's got 4 wheels to drive forward and backwards like we've seen in turning. And then it's got the one horizontal wheel that will allow the robot to drive sideways. So they'll use a different control, a joystick sideways or something, to make it drive sideways to help them sort of line up what they're trying to do, which is good if you're facing the hubs that you want to stack, but you're not lined up quite right, you can move it sideways and then put things where you want it, which is more difficult to do if you can only drive forward or backward. So this is the H drive. It does require 3 motors, which is not a big deal this year because we don't actually have to have a claw on things. And the obstacles, we have the blue bars here. Paul says that he thinks these can drive over. It kind of depends on how well the thing is set up, exactly where the Omni wheels are placed in relation to the other drive wheels, and how good the kids are driving. They can certainly figure out how to drive them over there, but this doesn't have the clearances what the 4-wheel generally does, because you have one wheel that's going to go sideways over this. And as you saw, we've got the smaller roller wheels. That's the actual wheel, so it's a small roller instead of the entire wheel, and if that's trying to roll over one of these bars, it may not go over as well. Something that we can talk to the kids about, and it may be harder to drive over the blue bars. Right?
yeah, I mean that's one of those examples where you want to let the kids learn and fail on their own, but you might not want to let them spend 3 months working on an H drive and get it perfected before they sit on the field and realize you can't traverse those terrain strips. So that's where being a coach, show them if they want to explore that, get them to build something relatively quickly, get it on there and start driving around and see how it performs. the thing that we saw in our summer camp that we already did this early this summer is one team built it and they put it directly in the center. So as it got to the bar, it literally had to lift the entire weight of the robot to get over that bar. And because the robot, when you lift the entire weight of the robot, it doesn't even have a tipping point, it couldn't go over the bar. But if they had moved it quite a bit further back, quite a bit further forward,
They could have moved it to this
it
same
would have
axle.
been, right, aided by the big wheels, and it would have been only tipping half the robot up in the front.
So they can move it to here or up here where it fit. This is what he's talking about, where it had to lift up the whole robot.
So because the rollers are, I think they're only about a 1/4 inch in diameter, and they're rolling over an 1/8 inch, or maybe it's half inch diameter over a 1/4 inch bar. They literally hit the bar about where they can't get over the bar. It's like hitting drive your car into a foot high curb. It won't go over probably.
Unless you're going fast. A couple other types of drive. This is an X drive. This has a motor on each wheel. Yes, it has a motor on each wheel. So it's a different drive system. It can be difficult to set up because of the angles that you want to set things up as. It can be difficult to control because of the controlling all 4 wheels. You can make the robot turn while it's moving up the field if you want. You can do all sorts of really cool stuff, probably not in 4th grade.
Yeah, you need custom programming to be able to control it correctly. You got to have a pretty advanced driver. Yeah, I wouldn't recommend this for any elementary team. Maybe an 8th grade team could.
This is very similar. It's got the tripod. It's got 3 motors instead of 4, 3 wheels. Again, it can turn while it's moving. It can do a lot of awesome stuff that's too hard to drive.
Do you have to program the remote for the H drive?
Yes, it would. Well, you could technically. So it's fine.
Well, not technically, you can, because you technically use the default driver control and just connect the straight drive to one of the like L or R buttons and like the top of the controller. But it's just it's just a lot more convenient to use.
It wouldn't be clear also with driving because if you push up to go left and down to go right, there's no way without custom programming to get a right and left coordinated with moving right and left. So.
It can be a challenge.
And what I'm getting at with all of these drivetrains, since they are different, unique, and not the standard, most of us are driving with driver control, the default coding, or default program. If you're adding another motor to the equation, you're going to most likely want to program it. Now you're kind of doing teleoperating type of controlling is you have and you can in ModKit, you can bring in a remote and customize
It's actually pretty easy. We're going to show you.
Yeah, but you just need to know you're no longer using driver control. And as Dane was saying, you have different ports on your brain that are already controlled by like those top buttons that are default that you could use, but it's not very intuitive to use those to go left and right. So,
Awesome. Another thing to talk to the teams about is how you're actually controlling the robot. We saw earlier, George was showing that lets us switch which directions forward and backward on the robot. You can also switch whether it's controlled by 1 joystick or 2. If you have it controlled by 1 joystick, when you slide the joystick to the side, the robot will turn. When you slide it forward and backward, it will move forward and backward. The other way, you're controlling basically one side or the other. Those are different ways it can be controlled. You'll have one kid that loves 1 joystick, which is great, except you have 2 drivers. So that's the kind of thing that you want to talk about and make sure that the whole team agrees on which way is best.
Yeah, and from our experiences, is always are relatively good if kids learn how to use it and get experience. So the worst thing you can do is decide in the middle of the season, after the kids have been driving around for a while, with 2 sticks to go to a 1 stick, because they're used to one way or the other. If you start them at the beginning of the year with 1 stick, they'll be good at 1 stick by the middle of the year, and definitely good by the end of the year. So pick a style and stick with it. It's probably the best way.
Your turn.
Oh, okay. What do we got time-wise? 7 minutes. Perfect. I didn't create that much stuff here. Okay, so Steve talked about the base of the robot and how we move the robot around the field. That's one of the big challenges, but then the other big challenge in this year's game is what do you do with the hubs? How do you score the hubs? One of the nice or interesting things about this year's game as compared to all the games in the past is you're limited to lifting 1 object at a time. So in past years, especially last year, Ringmaster, you had to pick up 10, 20 rings if you want to be competitive. And previous years, the crossovers, you had to pick up 4 to 6 balls. This year, for the first time ever, you can only pick up 1 at a time. And so the default style of intakes, like the pair of hooks here, or even that single set of squeezers, or even the squeezing arms of the ball bottom, all those will get you the ability to pick up as many hubs as the best teams will ever be able to pick up, because you're only allowed to pick up 1 at a time. In general, intakes come in 2 forms, and this is just not for this, but it's for everything. And one is active versus passive. Passive, Dane, show this. So passive, in essence, it means that you use a motor on it, right? Passive means that when he drives the robot, he puts it in a position and it takes it up. So the hub's been picked up by no motor interaction, right? You didn't take a motor. And because you're limited to 6 motors, because you want to do things quickly, if you've got extra motors, you'd like to put them on something else to do it quicker. If you're driving around the field at a certain speed, and you've got 2 more motors, you can throw the 2 more motors on your drivetrain and drive faster. To Steve's point, maybe you don't want to drive faster. Maybe you want to go faster forward and back and not turn as fast. You can create some custom programming to make it so it drives fast forward and turns slower. So, so that's a passive intake. And then active intake is like the flex spot here, has a motor that squeezes onto the part. This year's game objects are pretty big and pretty heavy and got a lot of geometry that allows you to do pretty good with a passive intake. So I foresee a lot of teams doing passive style intakes like this. But obviously, and even the example bot this year, this is last year's called Flex, the one called Stretch. The one called Flex this year has this exact same style of intake.
I think this year, one of the reasons you would want an active end of arm tool would be to tilt the hubs from being on their side. You might want to be able to stack them straight up. So you might want a way that you can grab the hub and turn it sideways. And so that might be a wrist kind of motion.
Yep. In fact, Dane, go over and stack up hubs in the corner goal there. So if you've got a first level of 4, that's the maximum. So the rules say you can't score any more than 4 in there. Even if somebody squeezes another in there, only 4 count. And now put 2 of them on there in the normal stacking way. And you're almost out of space. You can't really put another one on there, right? Now, what if you told them sidelines, like Steve said? No, I want just 2nd level. Don't go 3 levels higher. 2 levels lower. Put them all the way, all settings. If you can stack them sideways, you can get 4 on the 2nd level. You start doing math, you got to try to squeeze another bit now. Move out of the way so people can see. You actually get 5 on the 2nd level. Dane's actually figured out a way right now to score every hub in the game and not stack a 3rd level. It's only 17 hubs. Once you have 9 there and 8 over there, you got them all. So right, Steve has a very astute point that you may want to do something like that. Now, in the game example, they show big pyramids 4 levels high, but that's not practical. Nobody's going to want to do that because it's too hard. Right, like that. Too risky too. We've seen robots are hard to control. They lurch a little bit. It's so easy. These things slide on top of each other so easily, they'll get knocked off very easily. So the one concern I have in this game is how many times you're going to have a big stack and somebody will accidentally swing around and knock it over. 4 years ago, we had the stacking cube tower, and there were so many heartbreaking moments at the end where somebody had stacked a nice big tall stack up and the robot was celebrating and just spun around and knocked the tower. Ooh, that's painful. So, in general, we're talking about intakes, passive and active, and there's various reasons to do an active one. Another way is, and you didn't really mention this, but getting this on here requires some space around it. And if you've got other hubs nearby, it's hard to maybe get in there, but maybe not. But you could potentially have some kind of gripper that just grabbed the edge of it. So depending on what the strategy was, you might want an active intake that way. So once you've intaked the hub, you've grabbed hold of it, you want to lift it somehow. And so I just listed off a few lifting bar styles. So a 4-bar, does everybody know what 4 bars? You see the 4-bar? Okay. The 4 bars are here. One of my elementary kids said, there's only 3 bars in this 4-bar. 1, 2, 3. 1, 2, 3. No, those bars are 1. That's 1 bar. This is another bar. It just happens to be built out of multiple bars. Here's the 3rd bar, and here's the 4th bar. Right? So 4 bar it's parallelogram. 4 bars. And what happens to the parallelogram? These stay parallel, and these stay parallel. And this is anchored to the floor, so it's always vertical. Which means this is always vertical. That's why the 4 bar, and it's more complicated because of the 6 bar, which would have another intermediate bar right here and another bar right here. It's actually basically 2 parallelograms in the 6 bar, but it reaches higher.
Very good for this building thing because they always stay.
Stacking games are great for 4 bar because, especially if you want to keep whatever you're stacking oriented correctly. So 4 bar, 6 bar. Another version of that is called a chain bar, where you've got a central bar and hubs and chains on both ends. Any one of these things, if you go to YouTube and Google how to build a 4 bar or how to build a chain bar, you'll come up with 17 videos, really smart high school and middle school kids showing off their, either like the high school VEX program. Basically it's the same kind of stuff. It's metal with bigger components, but got the same kind of mechanisms. So you can learn a lot by Googling or YouTubing the builds of these things.
Just for your own reference, the 6 bar is very much like the 4 bar, except it lets you reach farther, generally.
Right.
So it does the same thing, keeps everything square, but it just lets it extend farther.
And then I put rack gear slider. VEX IQ has those little sections of rack gear that you can create the little slider things, and so I can envision some teams. We had a couple teams last year that had some sliders that allowed for perfectly linear sliding. With the 4 bar and the 6 bar, you get some of this travel here, right? Because it's kind of going through an arc. But when you have a linear slider, it goes like it's an elevator. It goes straight up and down. So those are some other ways to lift. And to stay on schedule here, I've got 1 minute to do plows. So the only way you can manipulate more than one object is if you keep them on the floor. The ruling says, as long as they're just on the floor or the terrain pieces or the scoring barriers, you're allowed to push them all at once. So certainly there's going to be a fair amount of designing the robot to create some kind of a corral or scoop of some sort on the front that can push 2, 3, 4 of those hubs all at once. And they designed these hubs specifically with a little chamfer on the bottom edge, so they can't easily go over here. Meaning that you've got to either take them around here, or you got to figure out some way to knock them over some way or tip them somehow and roll them on the floor. But these little things right here, they go over easily. So you can get them into the scoring team. So it's specifically designed with just the right shape to go over this and not go over that. And so plowing is going to be important because there's all these orange ones are all out throughout the field, and you want to get them over there en masse, and you can get them scored 3, 4 at a time into that low section, and then you'll start picking up the ones that stack up.
So can you lift this one and you plow?
Yes,
underneath
you
it?
can plow. Technically, you can lift one and plow all 16 other ones, if you somehow figure it out. Now, the size limitation makes it such that you can't build a very big corral without running out of space. So I don't foresee people pushing more than 3 or 4. And when you push 4 at a time, you can deliver all 4 all at once to here. You only have a minute, so there's a lot of time to be messing around with them. If you push 10, what are you going to do with 10 of them? Put 4 there and try to move the other.
Doesn't the rule say that also this, like because they have to be touching the ground, if you plow this, even if you're not touching this one, isn't that still?
That's indirectly lifting and moving that one. Yes, that's illegal. So you could not stack one. You could just stack one here, hold one in your robot, and then do this. Because both this one and this one are off the ground. It's all about contact with the ground. You have to stay in contact with the ground. If one can be controlled without being in contact with the ground, but a second one cannot. And that's including an indirect control.
We talked a little bit about making sure the robot fits in the size. Again, we want to, before we go to the tournament, make sure that it's not too big, so they don't have to redo anything at the event. One of the things that the rules say is the robot is allowed to get taller. At no point can it get longer than the 20 inches. One thing that you will need to do, because the kids will push this as much as they can, is you want to make sure the robot is as wide as possible when you measure it. So generally that means these bars that they have are mostly horizontal. That's pretty much going to be the maximum width for the robot. And measure it at that point to make sure that it fits within the size. You know, it's great that it fits in the square when it starts, but like Paul said, this robot swings out a little bit when it goes up. We want to make sure at its longest point that it still fits in the size. The more you can do that, the less headaches the kids are going to have at the events.
Now, if you designed the robot to fit within that 20, let's just use the 20 you're saying. But if you were, in the case of the hubs, if you're pushing them, that takes you outside the 20.
That's not your robot, that's the hubs, right? Yep. So even if the hub is sticking out, even if you're holding the hub so it's way out here, way out in front of the robot, that may be 23 inches. That's okay, your robot's still only 20 inches. Good question. Anything else?
But when they initially get to measure, it's at resting, which is that, right?
It needs to fit under the height. It needs to be less than 15 inches tall when it's down in the starting position.
Okay.
At any time during the match, it can't get longer than 20 inches.
So when we measure them, we have to look that up. And
Its longest distance, yeah, if you have any appendages that move out, whatever that longest distance.
It's termed maximum expansion. So about 4 years ago, they used to have unlimited expansion, and robots started getting wild and crazy and expanding half the field. And 3 years ago, with the shooting ball game, because you could just expand out and drop them into the bucket, they made horizontal expansion not unlimited, to a certain size spot. And it's been that way ever since. I don't think it'll ever change. I foresee horizontal expansion being in place. It's just too easy to fold out and become really big and do lots of work at once.
One other kind of a trick that the teams can do, the robot, when it starts the match, has to fit totally in the start square, which is 11 inches wide. And so the robot can't be wider than that. It has to, like I say, be able to fit in that start square. Well, actually, if I start the robot this way, I think this has to be down. I see how this went. But it's less than 11 inches wide. So it can start this way, start the match in this orientation, as long as it's under the height, which I don't think this is at the moment. But they don't have to start in this down orientation. So if they can move their arm up and the robot's under 15 inches, as long as we're starting in this square, we can start facing a different direction. We don't always have to start facing that way. Sometimes we've seen where teams will start facing the wall because they want to do some maneuver right off the bat. As long as they're starting in that start square, it doesn't matter what their orientation is.
Yeah, in general, the best way to think about it is that at any point during the match, from the point where it starts and start expanding, you have to be able to drop a infinitely high 11 by 20 box over it. So it can, you drop the box this direction, and then it changes shape such that it's wider this way and narrow this way, and then you can drop the box this way. As long as you can always get the box over the robot, it meets the no horizontal expansion.
The type of question that comes up, yes, if I have a robot that's 20 inches long, if I can shrink it down to 11 inches and then stretch out sideways, at no point was that out of bounds. I didn't fit in the same box all the time, but if at any point I put a box over it, it fits, and I can pull my arms in and stretch out again. And I still fit within those dimensions at all times.
As long as they are not expanding at the exact same time.
Right. Yeah, any other questions about robot build?
I would just quickly summarize. I think the order they presented it is the order I would ever design a robot, as in work on your drive base early, try to figure it out, and then move on. As that's your foundation, then move on to a lifting mechanism or an appendage, and then master that. It's a lot more difficult to modify your drive base once you already have a structure built above.
So let me talk to one more thing. I see this happen in all, especially younger kids, and I try to figure it out, but They want to build a drive base, and then they want to put a big flat horizontal plate on top of it, and then they want to snap stuff on top of that. And I tell them, the only reason the world has flat plates is for humans to walk on. Everything in the world, the floor we're standing on, the cars you drive, has structure that runs this direction. It has beams. And then we happen to put flat floors on top of it so the humans don't fall through the beams. If the human's not going to walk on it, you don't need a flat floor. So you want to have, and you look at all these robots, all have beams that run this way, and all have vertical stuff that are connected to those beams that lift off there. Nobody has any kind of floors in any of these robots. If you do that, that's just the point where it breaks. Right, you got all the weight up on this arm, it's only connected by way of snapping pins into a plate. You move a little bit, and it breaks off.
This one, to his point, in order for this beam to break off, the pins don't come out, they have to actually break. And so if you have the flat structure, the pins just pull out. And although it's really hard for us to do that when we want to get them out, when we don't want to get them out, they'll just fall right out. So this makes it so that this beam is attached directly to the structure. To get it to fall over, you have to break the pins.
And he's told our children that he gets on teams 1,000 times and they will still slap a giant flat plate on it.
It just makes sense, because the world has floors. The world I live in, everywhere you go, there's a floor to stand on.
In less than 1 minute, because I know we're over, can you answer the question of how do you prevent students from starting over completely? They don't like the idea, they don't like the design, they just want to take it apart and start all the way over. You're halfway through the season, you turn around and it's in parts. I know it's a loaded question, but I think it's the most common question I get, and it's very frustrating.
So
One thing about that, it's okay halfway through the season.
Yeah.
The week before the tournament, you got to go with what you got.
And I'm the same way. If you have time to start over, oftentimes the best solution is to start over. Learn from all the failings that you had. The best thing is if you got the parts, start building a new one and look at what was bad about that one and improve it on the new one. If you don't, then tear it apart and build again and know what the order is. But yes, there's a strategy management, and that comes into coaching. That's more of a coach's job than the student's job, especially at elementary level. They're not supposed to think about how many weeks they got until the next tournament. That's your job to do that. But you got to urge them, okay, we're a week away from a tournament here. We can't be tearing this apart. We can start thinking about and maybe building some mechanisms that are going to be the new robot the next week after that tournament's over, and we got a month to work on it, then we can do that.
Okay, so last year was my first year coaching, and when I came in, the kids that had been there before were saying, well, we already have this base that we built last year. Can we just keep the base and build off of that? What are your thoughts on keeping the base from last year and building off of that versus, because like the new kids wouldn't have any experience building a base at all if you kept the one from last year. But if they're just going to build another like H-shaped base again, should they keep it or should they build a new one?
So regardless of how well it worked last year, you can always build a better one. So if you force them to, no, you're a new team, you have new teammates, you should build a new one. Look at this, look at the shortcomings, and build something like this but better, it'll be better. One of the reasons I have students that have done this for 4 or 5 years in a row, and they start with a very good robot because they have all that experience of building all those versions before and know how to
Well,
get
the
started.
other thing is year from year, those pieces, that's what you don't see, and inevitably, we
Wear.
talked about how there's wear on it. That they don't see is that those plastic
Yeah.
squares are.
Take a robot apart, you'll see dust. All that plastic dust
From the year.
is the holes getting bigger and the robot getting worse.
We've had so many teams that have gotten to state, and all of a sudden their robot's not working, and it's because they've driven it so much.
With that extra dust and all that oblong in the holes comes extra friction, extra load on the motors, and at some point that extra load on the motors makes the motors not be able to overcome the loads. And like she said, had teams that had functional robots, and midway through a tournament, they stopped functioning. They just couldn't overcome all that friction because of all the wear.
The solution is to have them take it apart at the end of the season.
Yeah, when they walk in the first day, it's not an option.
Yeah.
Yeah, okay, are we ready to go?
Yeah.
What about I have young teens, 3rd and 4th grade, the new one, Flex Spot, if they make that off the, follow the diagram, make it, is it gonna be easy enough to modify it? Will they have to take it apart to modify it, or can they just add to it to modify it?
I think it's easy enough that you can add to that to modify, depending on what exactly they want to do.
Okay.
First of all, I strongly think all the teams should start by building one of those robots, a FlexBot, so that they have a working robot. Then they can start to think about what do they want to change on it. And yeah, it does usually start by, we're going to take these wheels off, make it a little wider, put some new wheels on.
That doesn't bother me, but what bothers me is them wanting to take the whole thing apart and start all over.
That is where we go back to how much time do you have? You know, we have 3 weeks until the tournament.
Exactly.
You have a working robot.
All right.
A lot of times what I'll do is I'll talk with them about, okay, we know what's wrong with this before the tournament this weekend. I want you to think this weekend what we can do to improve it. Look at some of the other robots, see what you like about them and how we can incorporate that into our next design.
Is this also good when maybe you assign like a team captain to your teams and that team captain kind of keeps those kids from going, oh, let's just tear it all apart. And you know, especially those veteran kids that are on your team, they can say, wait, let's
It's
take
definitely
it.
good if you can have somebody who's able to do that, who's able to recognize, you know, we need to kind of follow the schedule and not make that big change the last 2 weeks. I think we'll talk a little bit about that when we talk about building your team.